Welcome to today's deep dive. I want you, the listener, to prepare yourself right now. Seriously, get ready, because today we are going on a mission to completely, totally dismantle your visual intuition.
We really are. We're tearing it down to the studs.
Yeah, we are talking about entirely abandoning that comforting everyday idea of the universe. The one where reality is just a collection of solid physical marbles bouncing around in empty space.
The grade school solar system model.
Exactly. Every picture of an atom you've ever seen, every plastic model of the solar system you played with, we are taking a sledgehammer to that classical illusion today. Instead, we're diving headfirst into the literal source code of reality.
Which is heavy, but it's where the actual truth lives.
It is. We have this incredibly dense, profoundly structural set of notes and research in front of us today, all based on foundational quantum mechanics. But let me make a promise to you right up front. We are not just going to sit here and recite dry mathematical equations. That is not the goal.
No, nobody wants to just hear calculus read aloud.
Right. Our goal is to translate the absolute mathematical architecture of the universe into understandable, mind-expanding philosophy. We are taking the hardest concepts in physics and mapping them directly to how reality actually functions beneath the surface.
And that is a massively ambitious mission. But honestly, it's the only way to truly grasp what the physics is actually telling us. To do that effectively, we need a rigorous framework to hold all these mind-bending ideas together.
Because without a framework, it just sounds like magic.
Exactly. It sounds like science fiction. But the materials we are unpacking today provide this brilliantly structured lens for the analysis. They organize the chaotic, completely counterintuitive world of quantum mechanics into 5 recurring analytical categories that we will just keep coming back to throughout this deep dive.
Okay, lay them out for us. What are the 5 lenses?
First, we will be looking at first principles. These are the foundational axioms of the quantum system, the rules you just absolutely cannot break.
The bedrock.
All right. Second, we'll examine falsification filters. These are the ruthless mathematical logic gates that the universe uses to just flat out reject impossible realities. If the math doesn't pass the filter, that reality does not exist.
I love that concept, a built-in spam filter for reality.
It really is. Third, we will explore branching decisions. This is where the mathematics literally forces us to choose completely different computational paths depending on the physical scenario we find ourselves in.
Like a fork in the road of reality.
Yeah, precisely. Fourth, we will frame quantum measurement and learning as Bayesian updates, where new information instantly corrects our prior models of the universe.
So updating our beliefs in real time.
Yes. And finally, we will extract the metacognition. These are the profound philosophical takeaways that completely redefine our understanding of existence itself. This is not just a physics lesson. We are going to explore the epistemology of the universe.
Okay, let's unpack this, because I am ready to have my brain stretched.
Huh.
Just looking at the very first core concept we have here, this idea of the ontology mapping of wave functions and probability density. I am already fascinated by this term from the notes, computational diversion.
It's a great term.
It really is. It basically suggests that human brains are hardwired to track trajectories. Like, if I throw a baseball to you right now, your brain automatically calculates its arc, its speed, and exactly where it will land. We want to track the marble. We are obsessed with the marble.
We evolved to catch the marble or run away from the marble.
Right, survival instincts. But quantum mechanics comes along and says, no, you have to stop doing that. It forces us to offload all of that comfortable mental processing into solving partial differential equations. We have to completely strip away our visual intuition.
We do.
But why? Why is that stripping away so strictly necessary? Why can't I just picture a tiny, slightly blurry baseball?
Because the fundamental nature of reality simply does not consist of localized, solid objects following clean lines through space. That is a macroscopic illusion,
An illusion generated by our brains.
generated by our evolutionary need to survive on the plains of Earth, yeah? At the foundational level, the state of a physical system is uniquely and entirely described by a complex field evolving in multidimensional space. We call this the wave function, which is denoted by the Greek letter psi.
So no baseball, just a field.
Right. To understand why you really can't picture a blurry baseball, think of it this way. Classical mechanics is like watching a single spotlighted actor moving across a dark stage. You can always point to exactly where they are, and you can predict exactly where they're going to step next.
Very clean, very predictable.
Exactly. Quantum mechanics, on the other hand, requires you to ignore the actor entirely. There is no actor. Instead, you are observing a complex, shifting, mathematically precise lighting plot that covers the entire stage.
Oh, that's interesting. So the lighting plot is the reality.
The actor isn't moving from point A to point B. The probability of finding the actor at any given point is shifting like a fluid across the stage. The light represents the probability.
That is a brilliant way to picture it. We aren't tracking the actor at all. We are tracking the probability of the actor's existence at any given coordinate.
You're tracking the potential.
But how do we even begin to map our everyday concepts onto that, like momentum or position or speed? If I can't look at the actor's speed, what am I actually measuring when I look at the lighting plot?
Well, what's fascinating here is the mathematical elegance of the mapping. This is where our first principles come in. Classical variables, the things we can actually measure in a lab like momentum or kinetic energy, they do not map to static numbers anymore.
They aren't just numbers on a dial.
No, they map to linear operators acting within a mathematical realm called a Hilbert space.
Okay, pause. What exactly is an operator in this context?
An operator is essentially an instruction manual, a set of mathematical actions. The momentum operator, for instance, tells you to take the spatial derivative of the wave function and then multiply it by imaginary numbers and Planck's constant.
So it's a verb, not a noun. It's doing something to the wave.
Exactly. You apply this operator to the state, and the mathematical result gives you the observable information and the ultimate observation itself. That maps directly to the probability density, which is the absolute square of the wave function.
Absolute square.
Yes, because the wave function itself is composed of complex numbers. It has real and imaginary parts. So it isn't physically real in a way we can touch or directly measure with a ruler.
Wait. So the wave function has imaginary numbers in it.
It does.
That implies the foundational layer of reality is mathematically imaginary, and it only becomes real when we interact with it and square it. That is absolutely wild.
It fundamentally changes what the word real means. And this brings up a concept in the research called reverse thinking, specifically regarding the uncertainty principle.
Oh, right. Heisenberg's uncertainty principle. Most people have heard of this. The idea that you can't know exactly where something is and exactly how fast it's moving at the exact same time.
Yes, but the popular understanding of it is usually wrong.
Right. Usually this is explained as a measurement error, like the act of shining a light on a particle to see where it is actually bumps it and changes its speed. Human clumsiness.
A clumsy observer effect.
Yeah, but our materials treat this as an absolute mathematical boundary. It's not about clumsiness at all. Can you explain that reverse leverage?
The popular misconception is exactly what you just described, that uncertainty is just a result of clumsy human instruments. The thought is, if we just built a gentler, more precise microscope, we could see the particle's exact position and momentum without disturbing it.
Like sneaking up on it.
Right. But the mathematics entirely rejects this. The uncertainty is a fundamental, inescapable property of waves themselves. It has nothing to do with microscopes.
Give me an analogy for that. How is a wave inherently uncertain?
Let's use a sound wave analogy.
Yeah.
If you have a very short, sharp clap of sound, its position in time is incredibly well defined. You know exactly the millisecond it happened.
Right, a sharp spike of sound.
But because it's so short, it has no clear single frequency or pitch. It's just a broad spectrum of white noise. You can't hum the pitch of a hand clap.
Okay, that makes sense.
Conversely, if you have a long, beautifully sustained musical note from a violin, the pitch, the frequency, is perfectly defined. You know exactly what note it is. But its exact moment of occurrence is spread out over seconds. You can't point to a single millisecond and say, there is the note.
Oh, wow.
In quantum mechanics, position and momentum have this exact same relationship, which is dictated by the mathematics of Fourier transforms.
So position is like the sharp clap, and momentum is like the sustained violin note.
Exactly. As the spatial variance, meaning the uncertainty in position, approaches zero, meaning you know exactly where it is, the momentum variance absolutely must approach infinity. It is a rigid, unbreakable boundary of the universe's source code.
So if I squeeze the wave function to a single point in space to find its exact position,
its momentum representation physically explodes into an infinite superposition of all possible momenta.
if it explodes into infinity, that perfectly sets up the falsification filter our materials mention. The outline describes this filter as a logic gate that checks if a wave function is square integrable.
Yes, that is the technical term.
So if I'm translating this right, the universe has a built-in spam filter for impossible math, and infinity is the ultimate spam.
That is a highly accurate way to frame it. The falsification filter here is the normalization requirement.
Normalization. meaning it has to equal 1.
Right. Because the square of the wave function represents probability, and the particle must exist somewhere in the universe. The total probability of finding it anywhere from negative infinity to positive infinity must equal exactly 1. 100%.
Because it can't exist 110% of the time.
Exactly. If you have a mathematical solution to the Schrödinger equation where the wave function does not gradually approach zero as you move toward infinity, say, it just keeps growing, or it oscillates endlessly without fading,
Then what happens?
then the total integral will diverge to infinity. You cannot have an infinite probability. It's physically meaningless. Therefore, that mathematical solution, even though it perfectly solves the differential equation, cannot be normalized.
It's just garbage data.
It is deemed non-physical. The universe ruthlessly filters it out of existence. It simply cannot represent a real physical state.
Wow, it's just instantly rejected by the universe's operating system. So, assuming a state survives that filter, it normalizes to 1, and it actually physically exists. What happens when we, as observers, actually try to measure it?
This is where we hit the branching decision.
Right, the outline calls this a branching decision and a Bayesian update. I love this framing because it moves away from just pure math and starts looking at it through information theory.
Information theory is the best way to understand measurement.
So walk us through exactly what happens to the wave function at the precise moment of measurement.
This mechanic is arguably the most profound in all of physics. The branching decision works like this. As long as a system is isolated and unobserved, its state survives and evolves smoothly and deterministically according to the time-dependent Schrödinger equation.
It flows like a fluid.
It flows like a complex fluid, exploring all probabilities simultaneously. But the moment an external operator, an observation or measurement, forces an interaction, the system hits a branch.
A fork in the road.
It undergoes a radical nonlinear collapse. The calculation essentially rolls back. That smooth, spread-out wave function instantly reconstructs itself as a sharp, singular spike.
It becomes the hand clap.
Yes, it becomes an eigenstate of whatever operator you just used to measure it.
So if it was spread out like a cloud across the whole room and I set up a detector to measure its exact position, the cloud vanishes and instantly spikes at the exact spot my detector clicked.
It does more than just vanish and spike. It violently rewrites its own reality based on the interaction. Think of it like a Bayesian update in statistics.
Okay, refresh us on Bayesian updates.
In statistical analysis, Bayesian inference is all about updating your beliefs based on new evidence. You have a prior distribution, which is your initial best guess model of what's happening based on what you knew before.
Right, my working hypothesis.
In quantum mechanics, the evolving fluid wave function is your prior distribution. It tells you the odds of every possible outcome. But the instant you make a measurement, you gain absolute new information from the environment.
The detector clicks.
The detector clicks. And the prior distribution is instantly and absolutely corrected by the posterior result. The wave function updates to a delta function peak, reflecting the brand new reality that the particle is definitively at position X.
So bringing this to the metacognitive takeaway for this first concept, we really have to fundamentally change how we view the word reality.
We do.
Our notes point out that quantum uncertainty is not a limitation of our technology. It's not human ignorance. It is the physical limit of information coding at the universe's foundational dimension.
That is the core philosophical shift.
If I'm understanding this right, you're saying the universe itself does not know where the particle is until the measurement forces the Bayesian update.
That is exactly what the math implies. To demand that a particle have a definitive position and momentum simultaneously before you measure it is to demand something that the foundational code of reality simply does not support.
It's like asking what color the number 7 is.
Exactly. You're asking the universe to compute a state that violates its own falsification filters. The information literally does not exist until the interaction forces it to be rendered.
Like a video game rendering a tree only when you turn your character around to look at it.
Very much like that.
Okay, my brain is officially stretched. But wait, if reality is this constantly shifting fluid of probabilities and things only snap into focus when we measure them and force an update, how do we ever nail anything down?
It's a massive problem.
Right. How do we find stability in all that chaos? Is there a way to hit pause on the clock so we can actually study these things?
Yes, and this is where we look for a very specific computational diversion. The time-dependent Schrödinger equation, the one describing the fluid chaos, is incredibly powerful. But solving high-dimensional partial differential equations that are constantly changing in time is computationally brutal.
Brutal for humans doing the math.
Brutal for physicists and metaphorically brutal for the models themselves. So we change our strategy completely. We use a mathematical technique called the separation of variables.
Okay, how does that work?
If the potential energy of the system doesn't change over time, like an electron trapped in a perfectly stable electrical field inside an atom, we can strip time out of the equation entirely. We reduce the dimensionality.
We just delete time.
We split the problem. We separate it into a purely spatial part and a purely temporal part. The spatial part becomes the time-independent Schrödinger equation, which is essentially an eigenvalue problem.
So we freeze the frame.
Exactly. We are no longer tracking fluid chaos. We are looking for the stationary states, the specific, stable standing waves that can physically exist in that environment.
Okay, here's where it gets really interesting. To find those stable standing waves, the research says we offload the agonizing calculus into matrix algebra using ladder operators.
Yes, ladder operators are beautiful.
I just love the imagery of a ladder here. How does that offloading actually work? Are we literally climbing up and down energy levels?
The ingenuity of the physicists who figured this out is just remarkable. Let's look at systems like the quantum harmonic oscillator,
Which is what, like a pendulum?
essentially a microscopic pendulum or a vibrating chemical bond between two atoms. Instead of trying to solve the agonizing differential equations directly to find its states, we introduce algebraic constructs called creation and annihilation operators.
Or raising and lowering operators?
Right, more intuitively, raising and lowering operators. Think of the allowable energy levels of that vibrating chemical bond as the discrete rungs of a ladder. The raising operator mathematically boosts the system up one rung to the next higher energy state.
And the lowering operator steps it down one rung.
Exactly. By mapping the position and momentum operators into these algebraic matrices, we shift the entire burden of calculation. We don't need to do complex spatial integrals in calculus anymore.
We just do algebra.
We just apply simple algebraic rules, moving up and down the rungs of the energy ladder to find all the valid states of the system.
That feels like a massive cheat code for reality.
It is a profound shortcut.
But there's a deeply physical implication of this math under the leverage and reverse thinking header in our notes. If we are using this lowering operator to step down the energy ladder, rung by rung by rung,
Yes.
eventually we have to hit the floor, right? We have to hit the absolute bottom rung. What happens when we try to take a step below the floor?
That absolute floor is called the ground state. And this is where the reverse thinking provides incredible leverage. We know that energy cannot be negative infinity. There must be a physical bottom to the potential well.
You can't just fall forever.
Right. So we ask the math a direct question. What happens if I take the system in its absolute lowest possible energy state, the ground state, and I forcefully apply the lowering operator to it one more time?
What does the math say?
The universe's logical answer is that the mathematical result must equal zero. It must annihilate the state entirely because there is no lower rung to step to. The state ceases to exist.
Wait, if the state is annihilated and the equation equals zero, doesn't that mean the energy of that bottom rung is zero? Like a pendulum hanging perfectly straight down, not moving at all, zero energy.
You would naturally think so, but this is the vital distinction that absolutely shatters classical physics.
Okay, hit me.
When you set up that algebraic equation, the lowering operator acting on the ground state equals zero, and you solve that equation for the actual energy of that specific ground state, you find that the ground state energy is not zero.
It's not zero.
It is a positive, non-zero value. Always.
Wow.
This is the mathematical derivation of zero-point energy. The absolute mathematical boundary proves that a quantum system can never be completely at rest.
Even at absolute zero temperature.
Even at absolute zero temperature, in the deepest, darkest, coldest vacuum of intergalactic space, the harmonic oscillators of the universe are still vibrating with this baseline, irreducible zero-point energy.
The universe is just constantly humming.
The universe is always humming. It can never be perfectly still.
Oh, man. Because if it were perfectly still, its position would be exactly known, perfectly straight down, and its momentum would be exactly zero.
Which violates the uncertainty falsification filter we just talked about.
Everything connects. The rules of the source code just reinforce one another.
It's a perfectly consistent logic system. And speaking of falsification filters, there's another one specifically for these energy levels.
What's that then?
If you propose an energy level that is theoretically less than the absolute minimum of the physical potential well it's sitting in, the mathematics of the Schrödinger equation's second derivative dictates a specific behavior.
What does it do?
The wave function will aggressively curve away from the axis. It will diverge to infinity. And as we established earlier, Infinite wave functions cannot be normalized.
The spam filter catches it.
Exactly. Therefore, any energy state below the potential minimum is ruthlessly falsified and rejected by the logic gate of reality. It's forbidden.
So we have these stable surviving states, these stationary states that form the specific rungs of our ladder. Our materials bring up a Bayesian update trick here using Fourier techniques.
Projecting onto eigenstates.
Right. How does finding the rungs of a ladder help us predict the future of a particle? Because didn't we freeze time to find them?
We did freeze time to find the alphabet. Once you've found all the valid stationary states, the specific rungs of the ladder, you have essentially found the fundamental alphabet of that specific physical system.
Okay, an alphabet.
Any arbitrary, messy, chaotic initial wave function can be perfectly reconstructed by adding together the right amounts of these pure stationary states. It's much like how a complex, messy musical chord on a piano is built from pure single-frequency notes.
So you decompose the mess into pure notes.
Exactly. This relies on Fourier techniques. You mathematically project the initial messy state onto the pure eigenstates. This gives you a set of coefficients, which acts as a prior distribution of probabilities.
And how does that predict the future?
Because you know exactly how each pure stationary state evolves in time. They just spin their phase like a clock ticking away predictably. So you can instantly update your prediction for the system's future at any arbitrary time. You simply fast forward the clocks of the individual pure components and then sum them all back up.
Which leads to the metacognition of this section, and honestly, it's a bit of a brain twister. The text states that a stationary state is not actually frozen in time.
It sounds like a paradox.
It totally sounds like an oxymoron. If it's stationary, how is it not frozen?
It is a profound, incredibly counterintuitive truth. A stationary state has a definite exact energy. Because of that exact energy, its probability density, the actual physical shape of where the particle might be found if you measured it, is completely invariant.
So the shape doesn't change?
It does not change one iota as time ticks forward. If you map the probability cloud, it looks perfectly static, frozen.
Oh.
However, the underlying complex wave function is spinning its quantum phase at a massively high frequency, which is proportional to its energy.
I'm trying to visualize that.
Think of a perfectly balanced spinning top,
Yeah.
spinning so incredibly fast that it looks completely motionless. The probability is stationary, but the mathematical entity itself is in a state of violent, high-frequency rotation. This reinforces the idea that the algebraic structure of these operators and these phases exists fundamentally before the geometric structure of the space we observe.
If we are saying the math exists before the physical space, we really need to talk about where this math actually lives, because eventually we do have to talk about geometry.
We do. We have to build the stage.
And our research says we are now abandoning Euclidean space entirely for something called Hilbert space. Prepare us for this. We are leaving visual space behind.
We're leaving the coordinates of your living room entirely.
What are Dirac's bras and Kets, and why are we turning physics into pure logical symbols?
To truly understand quantum mechanics, you have to realize that 3D space, the Euclidean space of X, Y, and Z coordinates that we walk around in, is just one specific, highly limited way to view reality.
It's just what our monkey brains understand.
It's a localized projection. The true state of a quantum system exists as an abstract vector in an infinite-dimensional complex vector space known as Hilbert space.
Infinite dimensions, just saying that hurts my head.
Paul Dirac, one of the brilliant founders of quantum mechanics, recognized that the standard 3D coordinate math was getting way too clunky to handle this. So he invented a purely symbolic notation to manipulate this infinite dimensional space.
The bracket notation.
Yes, he literally split the word bracket into two pieces. The state vector of the system is represented by a ket, which is drawn as a vertical line and a right-pointing angle bracket.
And what does the ket represent?
It represents the abstract, unmeasured potential of the system. Its mathematical dual is the bra, a left-pointing angle bracket. When you mathematically bring a bra and a ket together, you compute an inner product.
And what does that output?
That spits out the probability amplitudes we actually care about. This notation allows us to perform massive calculations using pure linear algebra, completely divorced from having to visualize waves sloshing around in a physical 3D box.
It's pure logic.
Pure logic.
And the first principle here is fascinating. The notes say all observable physical quantities must be represented by Hermitian operators because they guarantee real number eigenvalues.
Yes, the Hermitian requirement.
Break that down for us. What is a Hermitian operator, and why does the universe absolutely insist on it for things we can actually measure?
Let's connect this back to the bigger picture. An operator, as we discussed, is an instruction manual, a mathematical action.
Mm,
In Hilbert space, it transforms one abstract state vector into another.
right.
But when we make a physical measurement in a real lab, like checking the readout on a digital thermometer or finding the speed of an electron, we absolutely require a real number.
You can't read an imaginary number on a screen.
Exactly. You can't look at an oscilloscope screen and read out a velocity of 5 plus 3i meters per second. Imaginary numbers don't show up on physical dials.
So how does the math fix that?
A Hermitian operator is a very specific class of mathematical matrix that has a magical property. No matter how complex the underlying infinite-dimensional space is, its eigenvalues, which represent the possible outcomes of a measurement, are strictly 100% guaranteed to be real numbers.
So the universe's falsification filter here is incredibly strict. If a mathematical operator is non-Hermitian, meaning it might spit out a complex number as an observable quantity, it is strictly filtered out of absolute reality.
It is mathematically exiled from the realm of observables. It cannot represent a real physical measurement.
And this geometric framework gives us a startlingly clear picture of what wave function collapse actually is.
It demystifies the collapse entirely.
Our notes say measurement collapse is a literal geometric projection. Give me a visual for that.
When you make a measurement, you are literally performing a geometric projection. Imagine shining a bright light on a highly complex three-dimensional object, and you are looking at its two-dimensional shadow on the wall.
Okay, I can picture that.
The measurement forces the abstract, multidimensional cat vector to violently project itself down onto the specific eigensubspace of the Hermitian operator you are using.
So the physical reality we observe in our labs
This is just a shadow cast by the Hilbert space vector when it hits the wall of our measurement apparatus.
That shadow analogy is deeply unsettling, but it makes so much sense. Now, what happens when we try to cast two shadows at the exact same time?
That's where things get complicated.
Like trying to measure the classic position and momentum problem we talked about earlier? Our notes introduce the commutator as a limit of precision. How does a commutator act as a lie detector for the universe?
The commutator is the ultimate mathematical lie detector for quantum compatibility. In classical physics, the order in which you measure things doesn't matter.
Right, if I measure your height, then your weight, I get the exact same numbers as if I measured your weight, then your height.
The variables commute. In quantum mechanics, operators don't always commute. The commutator of two operators, let's call them operator A and operator B, asks a very simple mathematical question.
Which is?
Does applying operator A, then operator B, yield the exact same results as applying operator B, then operator A? If you subtract the two sequences and the result is 0, they commute.
And what does it mean physically if they commute?
They share the same geometric eigenstates, meaning you can know both properties with absolute precision simultaneously. You can cast a perfect shadow for both.
But what if I subtract them and the result isn't 0?
If the commutator is non-zero, you have hit an incompatible boundary. This is the mathematical derivation of the generalized uncertainty principle we touched on earlier.
So it's baked right into the geometry.
Completely baked in. The degree to which they do not commute strictly defines the absolute limit of determining the two properties simultaneously. The non-zero commutator proves that the two properties require mutually exclusive geometric projections in Hilbert space.
You literally cannot cast a sharp shadow on both walls at the same time.
Exactly. The more precisely you project the vector onto wall A to get a sharp position shadow, the more blurred and smeared the shadow inevitably becomes on wall B for momentum.
That is just incredible. Depending on the operator, the notes say we hit a branching decision regarding the spectra, the possible measurement outcomes.
Yes, the math branch is hard here.
It says discrete spectra require matrix inversion and diagonalization, but continuous spectra, like momentum, require introducing the Dirac delta function to rebuild normalization standards.
That sounds like a massive mathematical headache.
It is a massive headache.
Why does the math branch so hard just because we measure momentum instead of energy?
It's because the physical nature of the boundary entirely changes depending on what you measure. If you're measuring the energy of an electron trapped in an atom, the allowed energies are discrete. They are specific, distinct rungs on the ladder.
Right, chunky energy.
The math reflects this beautifully with clean, finite matrices that we can easily diagonalize to find crisp, exact eigenstates. But if you measure the momentum of a free electron flying through the vacuum of deep space, The possible values are continuous. It could be literally any real number.
Smooth momentum.
Smooth, infinite momentum. Continuous states cannot be normalized in the traditional sense. Their wave functions extend to infinity without fading to zero.
Oh, wait. If they don't fade to zero, the falsification filter threatens to reject them entirely. Exactly. The universe is about to label free particles as spam. To save them from being deleted by reality's spam filter, Dirac had to invent the delta function.
What is that?
It's an infinitely high, infinitely narrow mathematical spike that allows us to force a new kind of normalization. It forces a complete rollback and redefinition of classical functions, just so we can handle states that aren't safely trapped in a box.
Which brings us to a really powerful metacognitive truth for this section on formalism.
It's the core realization of Dirac notation.
The notes say, physical laws are nothing more than geometric transformations in Hilbert space. The mathematics are the true entities, completely independent of how we choose to represent them.
Yes.
This implies that whether we look at an electron in terms of its position or its momentum, the underlying thing is exactly the same vector.
That is the deepest realization of Dirac's formalism. The vector in Hilbert space is the electron. Position and momentum are just different languages we choose to speak when we ask the electron a question.
Give me a way to think about that language difference.
Think of it like a poem. If you write a poem in English where you translate it perfectly into French, the ink on the page looks totally different. The sounds you make when reading it are different. But the core meaning, the abstract informational structure, is identical.
Or meaning is the vector.
The Dirac notation proves that the universe operates on an abstract informational structure that is completely independent of our human bias toward 3D coordinate grids.
Okay, speaking of our human bias toward 3D grids, we do actually have to live in one.
We do. We're stuck in 3D.
Eventually, we have to bring this beautiful, abstract Hilbert space math back down to the physical, three-dimensional world we actually interact with. But moving from one dimension to three isn't just 3 times as hard, it's exponentially worse.
It's a nightmare of complexity.
How do we handle that explosion of mathematical complexity?
This is why we must immediately deploy a massive computational diversion. If you try to solve the full 3D Schrödinger equation using standard x, y, and z Cartesian coordinates for something like an atom, the math becomes an intractable, tangled mess.
You just can't solve it.
It's virtually impossible. The solution is to leverage the geometric symmetry of the system. Atoms are generally spherical, so we abandon the XYZ grid entirely and execute a spherical coordinate transformation.
But we stop using cubes and start using spheres.
Right, we track the radius from the center and 2 angles of rotation. This brilliant maneuver allows us to completely separate the radial variables, meaning how far the electron is from the nucleus, from the angular variables, meaning how it orbits around it.
We split the problem again.
We split it, and the math channels into generating these incredibly beautiful, highly specialized mathematical constructs. Spherical harmonics for the angular part,
Right.
and Laguerre polynomials for the radial part.
And our materials point out a first principle here. The 3D rotational symmetry actually triggers the quantization of angular momentum.
Yes, symmetry forces quantization.
Just by the universe being spherically symmetrical, it forces angular momentum to be chunky, not smooth. How does empty space symmetry create chunks?
Let's visualize it. Think about a wave wrapping around the equator of a sphere. For the wave to be physically meaningful and stable, it must perfectly link up with itself when it completes a full 360-degree rotation.
And it has to meet its own tail.
Right. If it doesn't meet itself perfectly, if a peak meets a trough, the wave will destructively interfere and annihilate itself in a fraction of a second.
It cancels itself out.
This topological requirement that the wave must smoothly connect after one full rotation is the boundary condition that strictly forces angular momentum to be quantized.
So it has to be whole numbers.
It can only take on very specific integer-spaced values so that the wavelengths fit perfectly around the circumference. The rotational symmetry of empty space itself is what generates the rigid, stair-step nature of quantum rotation.
Wait, so earlier we used those ladder operators to step energy down to the ground state. Can we do the exact same thing with spin? Like if a particle is spinning, can we just keep stepping its angular momentum down or up until we hit a limit?
We absolutely do.
The notes mention searching for extrema and hitting a rigid boundary.
Yes, we use ladder operators for angular momentum, and the boundary we hit is a fascinating geometric limit. Imagine you have a spinning top. It has a total amount of spin energy. That's the total squared angular momentum.
Okay, the total spin.
Now you tilt that top and measure how much of that spin is pointing strictly upwards. along the z-axis. Simple logic dictates that the upward component of the spin can never, mathematically, be greater than the total spin of the top itself.
Because a piece can't be bigger than the whole?
Exactly. The math enforces this with ruthless efficiency. When we use our ladder operators to step up the z component of angular momentum, rung by rung, we eventually hit a ceiling.
And if we try to step up again?
If we try to apply the raising operator one more time, the math outputs 0, signaling we've hit the absolute limit. This creates a finite truncation.
Finite truncation, meaning it stops.
It proves that for any given orbital level, there are only a strictly limited finite number of allowable magnetic substates. The electron can only point its spin in a few highly specific quantized directions.
And there's another falsification filter here, specifically regarding the radial distance. How far the electron is from the nucleus.
We must check the falsification filter for the radial function at both extremes.
Where are the extremes?
Exactly at the origin, meaning inside the nucleus itself, and way out at infinity. If the mathematical solution causes the probability density to diverge to infinity at the nucleus, it's chopped off and discarded.
Filtered out.
And if it diverges at infinity, it's also discarded. This dual-ended logic gate is exactly why the principal quantum number, what we call n in basic chemistry, must be a whole integer.
Oh, that's why n is 1, 2, 3.
Only those specific integer values produce mathematical functions that cleanly approach 0 at both extremes, surviving as valid physical states.
Let's bring this to a real-world application, the hydrogen atom.
The classic test case.
The classic model we all learn in grade school is the solar system model, a little electron planet orbiting a proton sun. Our outline sets up a branching decision here. It says a pure Coulomb force generates the exact hydrogen solution, but if spin is involved, we have to roll back the pure spatial function and use Clebsch-Gordan coefficients.
Yes, the math gets incredibly tangled here.
Unpack that for us. Why is the solar system model wrong, and what is making the math so complicated?
The grade school solar system model is a useful fiction, but it is ultimately entirely wrong. When we solve the pure electrical attraction, the Coulomb force, between the proton and the electron, assuming they are just simple point charges, we get a beautiful, exact mathematical solution.
That sounds great.
It is, but electrons have an intrinsic internal property called spin. It's like they possess their own tiny internal quantum bar magnet.
So they aren't just points.
No. The electron's orbital motion around the nucleus creates a magnetic field, and its internal spin magnet interacts with that field. This is called spin-orbit coupling.
It interacts with its own motion.
Exactly. Because of this, we hit a branching decision. The pure spatial wave function is no longer accurate enough. We must forcefully roll back our calculation and mathematically stitch together the electron's movement through space with its internal spin state.
And that's where these Clebsch-Gordan coefficients come in.
Yes. Think of it like trying to perfectly balance a spinning top while you are riding on a spinning merry-go-round.
That sounds nauseating.
The two different spins, the top itself and the merry-go-round, interact and fight each other, creating complex wobbles. We use incredibly complex matrices called Clebsch-Gordan coefficients to perfectly couple the orbital angular momentum and the spin angular momentum into a single, unified total angular momentum state.
It's the mathematical tool we use to figure out exactly how the wobbles align.
It is exactly that.
And the Bayesian update comes into play when we stick this whole complex wobbling atom into an external magnetic field, right?
This is known as the Zeeman effect.
What happens in the Zeeman effect?
If we take our mathematically perfect isolated hydrogen atom and drop it between the poles of a strong external magnet, our prior model is instantly falsified. The external magnetic field grabs hold of those tiny electron spin magnets and physically wrenches their energy levels apart, depending on how they are aligned.
So it literally breaks the energy levels.
States that used to have the exact same energy are violently split into distinct separate lines if you look at them through a spectroscope. We have to update our prior no-field models to account for this newly introduced asymmetrical energy landscape.
Which perfectly leads to the metacognitive realization for this section. The hydrogen atom is not a solar system. The text calls it a 3D standing wave, where continuous space is topologically sliced by discrete quantum numbers.
It's a profound shift in visualization.
Topologically sliced, what does that look like?
When you look at the true shape of a hydrogen orbital, you do not see a little ball on a track. You see complex glowing clouds of probability.
Yeah,
some look like solid spheres, some look like dumbbells, some look like complex multi-lobed clover leaves.
Like balloons tied together.
Very much like that. There are three-dimensional standing waves, much like the vibrating patterns you see if you sprinkle sand on a vibrating drumhead, but vibrating in empty space. The quantum numbers are literally topological slicing instructions.
They dictate the shape.
They dictate exactly how many radial nodes and angular slices cut through the probability cloud. Atoms are not tiny machines with moving parts. They are pure geometric resonant cavities holding trapped probability waves.
Trapped probability waves, that is going to stick with me. So what does this all mean when we start adding more stuff? One hydrogen atom is cool, but the universe is made of septillions of atoms all interacting.
Now we have to build matter.
And immediately our notes tell us we have to eradicate the numbering illusion. What is the numbering illusion?
If you have two billiard balls on a table, a red one and a blue one, you can easily track them. Even if you paint them both perfectly white, you can keep your eyes on them as they bounce around and say, this is ball 1 and that is ball 2.
Right, you just watch them move.
This is the numbering illusion. In classical physics, particles always have a distinct continuous trajectory, so they always possess a distinct identity over time. Quantum mechanics forcefully eradicates this idea.
How so?
The first principle here is absolute mathematical indistinguishability. If you have two electrons, they are fundamentally perfectly identical. There is no microscopic scratch, no serial number, no difference in mass or charge that can tell them apart.
They are perfect clones.
Perfect clones. And because they do not have solid trajectories, remember the shifting lighting plot on the stage, their probability clouds overlap. Once those clouds overlap, the universe literally forgets which electron is which.
The universe forgets.
You cannot say electron A is here and electron B is there. You can only say there are two electrons in this general region.
And because of that, the text says we can't just multiply their Hilbert spaces together like simple math. We must forcefully filter the states through symmetric or antisymmetric projection operators.
Yes, we branch into the rules of identity.
This branches off into the two great architectures of the universe, fermions and bosons. Break down this mapping for us.
This is where mathematical symmetry dictates the entire physical structure of the universe. All particles with half-integer spin, like electrons, protons, and neutrons, are classified as fermions.
Fermions, okay.
The universe demands that their combined wave function must be entirely antisymmetric. This means if you mathematically swap the positions of two identical fermions, the entire wave function must multiply by -1. It flips its sign.
And bosons.
Particles with integer spin, like photons of light, are bosons. Their wave function must be completely symmetric. If you swap two identical bosons, the wave function remains exactly the same. Multiply by +1.
Okay, multiplying by -1 doesn't sound like a massive reality-altering big deal until we look at the deep analysis of the Pauli exclusion principle. Because the text says we need to look at what happens when two fermions try to occupy the exact same quantum state.
This is the crux of why matter exists.
Walk us through this absolute zero subtraction, because I think this is where things get completely crazy.
This is arguably the single most important mathematical operation for human existence. Let's test the antisymmetric requirement. We try to force two identical fermions, say two electrons, into the exact same quantum state in the exact same location with the exact same spin.
He forced them together.
Because they are fermions, the total wave function is constructed by taking the state of particle 1 and particle 2 and subtracting the swap state of particle 2 and particle 1.
Because of the -1 flip.
Exactly. But since the states are perfectly identical, you are mathematically subtracting a value from itself. State x minus state x. The mathematical result is exactly, absolutely zero.
It's just a blank void.
It is a complete void. The wave function literally annihilates itself. This is the mathematical proof of the Pauli exclusion principle. The probability of finding two identical fermions in the exact same state is mathematically zero.
This falsification is the rigid structural support of the entire universe. It's the only reason matter takes up space. Let's really expand on that, because right now, my hand is resting on a wooden desk.
Yes.
It feels solid, but we know atoms are mostly empty space.
Yeah.
Why doesn't my hand just pass right through the desk? What would happen if the electrons in my hand and the desk were bosons instead of fermions?
If electrons were bosons, your hand would phase right through the desk.
Just pass right through.
Bosons love to share states.
Mm-hmm.
If electrons were bosons, all the electrons in an atom would just cascade down into the lowest energy ground state, piling on top of each other infinitely. Atoms would shrink to practically nothing.
So no chemistry.
Chemistry would not exist because there would be no valence electrons reaching out to form bonds. Solid objects would pass right through one another. The rigid volume of the desk you are leaning on is not caused by solid marbles bumping into each other.
What causes it then?
It is maintained by this continuous absolute mathematical rejection of symmetric states, by the universe's falsification filter. The fermions in your hand are mathematically forbidden from occupying the same space as the fermions in the desk.
Because if they did, the math would equal 0 and they would cease to exist.
Exactly. That mathematical prohibition is what you feel as physical solidity.
That is mind-blowing. The math actively prevents reality from collapsing in on itself. So how does the universe keep track of this? The outline mentions the Slater determinant for fermions and macroscopic ground state condensation for bosons.
Because fermions cannot occupy the same state, they must stack upwards. When you build a heavy atom, the first two electrons take the ground state, one spin up, one spin down.
And the third one.
The third electron is strictly forbidden from entering that state, so it must occupy a higher energy orbital. Then the next, and the next. The mathematical tool to ensure the wave function remains perfectly antisymmetric as you add more and more electrons is a matrix structure called the Slater determinant.
The Slater determinant, what is that practically?
Think of it as the universe's unimaginably strict seating chart. This simple mathematical matrix operation literally forces the orbital structures that build the entire periodic table of elements.
It dictates all of chemistry.
All of chemistry, and by extension, the complex solid-state band structures that make semiconductors, computers, and modern electronics possible. It all comes from this seating chart.
And bosons don't have a seating chart.
Bosons face no such restrictions. If you cool a gas of bosons down near absolute zero, they will all collapse into the exact same ground state, forming a macroscopic quantum object called a Bose-Einstein condensate.
Where millions of atoms just merge.
Millions of atoms lose their individual boundaries entirely and behave as a single, giant, unified quantum wave.
And this leads to a Bayesian update called the exchange force. Our notes say this is an effective attraction or repulsion born purely from wave function symmetry, totally updating our classical Coulomb models. What is an exchange force? Is it a new physical force like gravity or magnetism?
The most beautiful part is that it is not a new fundamental force at all. It is a purely statistical, emergent phenomenon.
Okay, emergent from what?
Because the spatial wave functions of fermions must be antisymmetric, the math essentially forces their probability clouds to spread apart, creating a mathematical hole between them.
A hole in probability.
They statistically avoid each other more than their standard electrical repulsion would predict. It acts exactly like an extra repulsive force, pushing them apart.
Even though there's no actual physical field pushing them.
Exactly. Conversely, bosons are statistically driven to bunch closer together than classical physics allows, acting like a phantom attractive force. We have to take our prior models, which only calculated standard electrical push and pull, and run a massive Bayesian update.
We have to add in the phantom pressure.
We include this exchange force, this phantom pressure, generated entirely by the universe, enforcing geometric symmetry.
And the metacognitive conclusion here completely shatters the idea of individual particles. The text says different particles don't actually have individual identities. They are merely different permutation combinations of the underlying quantum field's excited states. Let's linger on that. What does that actually mean for the stuff we are made of?
If you look at a digital billboard, you might see a picture of a car moving across the screen.
Sure.
But nothing physical is actually moving across the screen. Individual pixels are just lighting up and dimming in a coordinated pattern. Quantum field theory tells us reality is the exact same way.
We are just pixels.
There is a universe-spanning electron field. What we call an electron is just a localized packet of energy and excitation within that field. If electron A and electron B swap places, the universe doesn't track two marbles crossing paths.
It just changes the lights.
It just dims one pixel of the field and brightens another. The particles are just manifestations of the field's symmetry rules. You aren't made of individual eternal marbles. You are made of localized ripples in universal fields.
Incredible. I feel like I need to look at my own hands differently now. But speaking of symmetry, let's look at section 6 of our materials. Group theory and the topographical map of conservation. I always marvel at how physicists know certain things are always conserved, like energy or momentum, without having to solve impossible equations for every single particle in a complex system, like a whole galaxy.
It would be impossible to compute that particle by particle.
So how does group theory act as a computational diversion here?
When a system gets too complex, solving the Schrödinger equation directly becomes completely impossible. So we bypass the equations entirely by studying the geometry of the system's environment. Group theory is the mathematics of symmetry.
Okay, so we look at the shape of the rules.
Instead of asking why something is conserved by calculating billions of microscopic interactions, we look at the Hamiltonian operator, which is the total energy matrix of the system. We calculate the mathematical commutator of the Hamiltonian with a specific symmetry group generator, like a rotation matrix.
And if they commute?
If the commutator is zero, it means the energy is completely unaffected by that specific transformation. The symmetry directly locks in the physical conclusion. The corresponding physical property must be absolutely conserved. No complex calculus required. The geometry dictates the physics.
And the outline maps this to Noether's theorem in the quantum realm. Emmy Noether is an absolute legend in physics. Break down this mapping for us. How do space, time, and rotation literally map to conservation laws?
Emmy Noether proved what is arguably the most elegant theorem in all of physics. It states that every continuous mathematical symmetry in nature has a corresponding, rigidly conserved physical quantity.
Give me an example of a continuous symmetry.
Now, the quantum realm, if we apply a spatial translation operator, meaning we mathematically slide our entire experiment 3 feet to the left and the underlying physics does not change, then the momentum of that system must be perfectly conserved.
So space symmetry equals momentum conservation.
Yes. If we apply a time translation operator, meaning the laws of physics are the exact same today as they will be tomorrow, then the total energy of this system must be perfectly conserved.
Time symmetry equals energy conservation.
And if the system possesses rotational symmetry, meaning it looks the same no matter how you spin it, then angular momentum is strictly conserved. Conservation laws are not arbitrary rules imposed from the outside by some cosmic traffic cop.
They are just the shape of reality.
They are the unavoidable, inevitable consequences of the universe's geometric symmetries.
The text mentions leveraging discrete symmetries like parity inversion to search for extreme boundaries. What is parity inversion, and how does it act as a falsification filter with selection rules?
While translation and rotation are continuous symmetries, meaning you can slide or rotate something by any tiny fractional amount, parity is a discrete symmetry. It is all or nothing.
What does a parity inversion look like?
It is the mathematical equivalent of flipping the universe inside out through a mirror. You change every x, y, and z coordinate to negative x, negative y, and negative z.
A total mirror flip.
Some wave functions look exactly the same after this mirror flip. We call them even parity. Some wave functions flip completely upside down. We call them odd parity.
Okay, so where is the filter?
The falsification filter comes in when an atom tries to emit a photon of light and jump from one energy state to another. To calculate the probability of this jump, we compute a transition integral.
And if the math doesn't line up?
If the initial state, the final state, and the transition operator do not combine to form an even parity symmetry overall, the integral mathematically evaluates exactly to zero.
So the jump can't happen.
The probability of that atomic jump happening is absolutely zero. It is fundamentally forbidden. These are called the selection rules of spectroscopy. The universe filters out any atomic transition that violates its internal parity symmetry logic.
But what happens when symmetries are broken? Because the real world isn't a perfect, flawless mirror. Our notes describe a branching decision here. High symmetry guarantees degenerate states, but symmetry breaking forces a rollback and inevitably causes energy levels to split. What does it actually mean for a state to be degenerate?
Degenerate in quantum mechanics doesn't mean morally corrupt. It means multiple different physical states share the exact same energy level. They are parked on the exact same rung of the energy ladder.
Why do they share a rung?
High symmetry mathematically guarantees degeneracy. For instance, in a perfectly spherical atom, an electron orbiting around the x-axis, the y-axis, or the z-axis all have the exact same energy because all directions are equivalent in a perfect sphere.
But if we break the sphere?
If you break that symmetry,
Right.
say, by placing the atom between two powerful electrical plates, establishing a definitive up and down, the spherical symmetry is destroyed. The branching decision kicks in.
So the states can't share the rung anymore.
You must roll back the state-space structure. Because the environment is no longer perfectly symmetric, those three orbits are no longer equal. The once degenerate, single energy level violently splits into three distinct, separate energy levels.
And that splitting is exactly how we run a Bayesian update. The text says, observing which reactions happen or are forbidden allows us to infer backward, updating our prior knowledge of what hidden symmetries the Hamiltonian must possess. We use the broken pieces to reverse engineer the original shape.
Experimental physicists shoot lasers at atoms and observe the spectral lines, the specific colors of light absorbed or emitted. If they see a single spectral line suddenly split into three distinct lines when they apply a magnetic field, they perform a Bayesian update.
They learn something new about the inside.
The posterior data, the split lines, updates their prior model, proving definitively that the internal Hamiltonian of that atom possesses a specific hidden symmetry that the magnetic field just broke. The breaking of the symmetry reveals the internal structure of the atom.
So the metacognitive conclusion for group theory is the evolution of physics is fundamentally just the projection of symmetry group representation theory onto the dimension of time. The universe is just geometry unfolding on a clock.
It's an incredibly unified, majestic view of reality. It strips away the messy details of individual particles and forces and reveals that the beating heart of reality is just a pure, abstract scaffolding of mathematical symmetries projecting themselves forward.
Okay, speaking of messy details, let's dive into the next section. Time-independent perturbation theory and approximating reality. Because as beautiful as those perfect symmetries are, real life isn't perfectly symmetric.
Real life is incredibly messy.
We have atoms with complex spin-orbit coupling, interactions with other atoms, external fields fluctuating. How does quantum mechanics deal with messy reality when we can't solve the exact equations? Because if the math is too hard, we have a problem.
This raises perhaps the most practical question in all of physics. What do we do when the math is simply too hard to solve exactly?
What's the trick?
We abandon the pursuit of absolute, pristine analytical solutions. That might sound like defeat, but it's actually our most powerful computational diversion. We turn to perturbation theory.
Perturbation theory, meaning we perturb it, we poke it?
Yes. Instead of trying to solve the impossibly complex real-world system from scratch, we start with a highly simplified, perfectly symmetrical model that we can solve exactly, like the basic hydrogen atom. This is our unperturbed ground state.
The ideal version.
Then, we treat the messy, real-world complexity as a tiny, annoying perturbation, a slight nudge to the perfect system. The first principle here is the analytic Taylor expansion. Assuming the perturbation parameter is incredibly small, we calculate a series of mathematical corrections.
Like fine-tuning it.
Exactly. A first-order correction, a second-order correction, and so on. And we add them to our perfect model to slowly approximate reality.
It's like tuning a guitar. You don't rebuild the whole guitar from scratch if it's slightly out of tune. You just take the perfect ideal of the string and apply a tiny rotational perturbation to the tuning peg to bring it closer to reality.
That is a perfect analogy.
The outline maps real-world effects like the Zeeman and Stark effects to adding a perturbation Hamiltonian matrix. How do we leverage what the notes call good quantum numbers to make this matrix math manageable?
When you add that perturbation, let's say an external electric field causing the Stark effect, you represent it as a new modifying matrix added to your perfect Hamiltonian. The problem is calculating the corrections requires integrating this new matrix across all the possible quantum states.
It sounds hard.
This is brutally difficult if the states are degenerate. But we leverage good quantum numbers. A good quantum number is associated with a physical property that is still rigidly conserved even after the perturbation is applied.
It survives the nudge.
By carefully choosing our mathematical basis to align with these good quantum numbers, we force the messy, terrifying perturbation matrix to become diagonal.
Diagonal, why is that better?
A diagonal matrix is vastly simpler to compute. All the off-diagonal chaotic cross terms drop to zero. It's the ultimate mathematical leverage to extract the energy corrections with minimal computational pain.
But there is a breakdown boundary. The text warns us that when the energy difference between unperturbed states approaches zero, the denominator in the second-order correction explodes. The math crashes. What does that mean? How does math just crash?
This is a classic mathematical boundary condition. The formula for the second-order energy correction requires you to divide by the difference in energy between two states. Energy of state N minus energy of state M.
Okay, division.
If those two states are degenerate, meaning they have the exact same starting energy, that difference is exactly zero. You end up trying to divide by zero in the equation.
And you can't divide by zero.
The formula yields infinity. The math aggressively crashes, signaling the absolute boundary where standard perturbation theory fails completely. The universe is telling you, your assumption that the perturbation was just a tiny, negligible nudge is false when the states are degenerate.
And that triggers a falsification filter. If degeneracy exists and the perturbation matrix has non-diagonal elements, the simple first-order formula is rendered useless and filtered out. We must switch to solving secular equations. What is a secular equation?
The branching decision forces us to abandon the simple approach entirely. Because the states are degenerate, the tiny perturbation isn't just slightly shifting the energy, it is violently mixing the degenerate states together.
It's tangling them up.
We must reconstruct a complete set of commuting observables to lift the degeneracy before we can proceed. We set up a secular equation, which is essentially a mini-matrix eigenvalue problem specifically for those degenerate states.
To untangle them.
We force the map to figure out exactly how the perturbation breaks the symmetry and splits the energy level apart before we can calculate any further corrections. It's a way of mathematically untangling the mixed states.
This whole process sounds like an endless cycle of fine-tuning. The Bayesian update cycle mentioned here says we take experimental data of fine structure, like relativistic corrections and spin-orbit coupling as a posterior, and use it to continuously add higher-order perturbation terms to our prior Hamiltonian. It never really ends.
It is an endless, asymptotic pursuit of the truth. Our very first model of hydrogen was just simple electrostatic attraction. Then experiments showed the spectral lines were actually slightly fuzzy.
So we ran an update.
We ran a Bayesian update. We added a perturbation for the electron's relativistic speed. Then new, better experiments showed the lines were actually split in two. Another update. We added a perturbation for spin-orbit coupling.
And it just keeps going.
Then experiments showed an even tinier splitting. Another update. We added a perturbation for quantum electrodynamic vacuum fluctuations, the Lamb shift. We constantly refine our prior model with new experimental posteriors, getting closer and closer, but never reaching perfection.
And that delivers a deeply humbling metacognitive insight. Absolute precision only exists in idealized math. Our understanding of physical reality is a process of infinite series convergence, constantly adding tiny tuning factors to our axioms. We never reach perfect reality. We just keep adding more decimal places to our approximation.
Physics is the art of knowing exactly how wrong your model is and calculating precisely the right perturbation to make it slightly less wrong next time.
Okay, but what happens when the system is so complex that even perturbation theory crashes and burns? Say we are looking at multi-electron atoms like helium or heavier where the electrons are constantly repelling each other in a chaotic dance. That brings us to Section 8, Variational Principle and WKB Semi-Classical Boundaries.
Where we have to get creative.
The outline introduces the ultimate computational diversions, guessing the ground state. How is guessing a legitimate mathematical strategy in quantum physics?
When analytical solutions are impossible and perturbation theory fails because the interactions aren't tiny, we invoke the variational principle. The first principle here is one of the most powerful theorems in quantum mechanics.
What does the theorem state?
It states that the expectation value of the energy for any completely arbitrary guessed trial wave function in Hilbert space is strictly greater than or equal to the true ground state energy of the system.
Wait, hold on. So I can literally just make up a mathematical function out of thin air, plug it into the Schrödinger equation, and the math guarantees me that the energy number I get will always be higher than the real answer.
As long as your guess function satisfies the basic falsification filters, like normalization and the boundary conditions, yes. The energy you calculate will always be an upper bound.
Why is it always higher?
Because the true ground state is the absolute lowest possible energy state of the universe for that system. Any deviation from the perfect true wave function, any imperfection in your guess, inevitably costs energy, pushing the result higher.
So how do we use that to find the real answer?
So the computational diversion is this. We don't just guess blindly. We create a trial function containing several adjustable, flexible parameters. Then, we use the leverage of calculus to tune it.
The notes say we leverage derivatives to force out the absolute lower bound. Explain that mapping to the helium atom, because helium is notorious for breaking the simple math.
Let's take helium. 2 protons in the nucleus, 2 electrons orbiting. The electrons repel each other, which makes the exact math impossible to solve analytically. So we guess a trial function that looks like 2 individual hydrogen wave functions.
Okay, a reasonable guess.
But we replace the nuclear charge, which should be exactly 2, with an adjustable parameter, let's call it Z effective, the effective shielding charge. Because the electrons block each other's view of the nucleus, they don't feel the full charge of 2.
They shield each other.
We calculate the energy expectation value using this parameter, which gives us a complex algebraic equation. We then take the partial derivative of that energy with respect to Z effective and set it equal to 0.
What does setting it to 0 do?
This calculus maneuver forcibly finds the exact value of Z effective that minimizes the energy. We are mathematically turning the dial until we hit the absolute lowest possible energy our trial function can reach. It won't be perfectly exact, but it is an incredibly tight, highly accurate approximation of the true ground state.
That is brilliant. You just squeeze the math until it yields the best possible answer. But our research also mentions the WKB approximation, which is used for a different kind of problem. Semi-classical boundaries. What does WKB do, and where does it break down?
While the variational principle is great for finding the ground state energy, the WKB approximation, named after Wenzel, Kramers, and Brillouin, is used when an electron is moving through a potential landscape that changes very slowly compared to the electron's wavelength.
Why is it called semi-classical?
It's a semi-classical approach because it treats the quantum wave almost like a classical particle accumulating phase as it moves. The computational diversion here is using classical momentum to approximate the quantum amplitude and phase.
But there is a severe reverse boundary where this logic collapses. The outline says at the classical turning point, where total energy equals potential energy, the classical momentum drops to zero. And this causes the quantum amplitude to diverge. Walk me through that.
Think of a skateboarder rolling up the curved side of a half-pipe.
Okay.
As they go higher, their potential energy increases and their kinetic energy drops.
Mm-hmm.
Eventually, they hit the exact height where their total energy equals the gravitational potential energy.
They stop.
At that instant, their speed, their classical momentum, drops exactly to zero. They stop for a split second before rolling backward. This is the classical turning point.
Right.
But in the WKB approximation formula, the quantum amplitude is inversely proportional to the square root of the momentum. So when momentum drops to zero at that turning point, you are dividing by zero in the formula.
No, another divide by zero math crash.
The quantum amplitude mathematically explodes to infinity. This explicitly defines the boundary where the semi-classical approximation totally breaks down. You cannot use classical momentum to predict quantum behavior exactly at the point where the particle stops and turns around.
So how do we survive this mathematical breakdown? Our materials say we hit a branching decision, the wave function collapses, and we must roll back and introduce airy functions to stitch the regions together. We literally have to suture the math.
It is a phenomenal piece of mathematical patching. Because WKB works great deep in the allowed zone where the skateboarder is moving fast, and it works great deep in the forbidden tunneling zone on the other side of the wall, but it explodes right at the boundary wall itself.
So what do we do at the wall?
So right at that classical turning point, we branch away from WKB. We zoom in incredibly close to the turning point, where the potential curve looks like a straight slanted line. We solve the Schrödinger equation exactly for that slanted line, which generates special mathematical solutions called airy functions.
And they don't explode.
These functions don't diverge to infinity. They smoothly transition from an oscillating wave on one side to an exponentially decaying tail on the other. We use these airy functions as connection formulas, literal mathematical stitches to sew the WKB solution from the allowed region safely across the turning point boundary and connect it to the WKB solution in the tunneling region.
We literally have to suture the classical and quantum worlds together with special functions to prevent infinity from breaking the math. And the Bayesian update here is how we apply this to complex molecular bonds, constantly refining our trial functions and connection formulas to update our numerical models of how multi-body systems actually hold together.
The metacognitive bridge for this section is a great summary of this idea. Classical and quantum mechanics are not disconnected worlds separated by an impassable wall.
They bleed into each other.
Macroscopic classical physics is just the statistical limit projection that emerges when Planck's constant approaches zero relative to the system, or when high-frequency quantum oscillations are filtered out by destructive interference. It's a continuum.
You don't live in a classical universe.
You live in a quantum universe where the quantum weirdness is happening so incredibly fast and is so densely averaged out by the sheer number of particles that it statistically smooths out into the classical Newtonian world you perceive.
Okay, let's pivot to section 9. Partial wave analysis and the Born scattering operator. So far, we've mostly been talking about trapped particles, electrons stuck in atoms, or potential wells. But what about free particles smashing into things? We can't see the inside of a proton with a microscope. Our materials call this probing the invisible. How do we know what atomic structures look like if we can't look at them?
This is the essence of scattering theory, which is arguably the most important operational tool in all of high-energy physics. If you want to know what an invisible sculpture looks like in a pitch-black room, you throw thousands of ping-pong balls at it and measure the angles at which they bounce off.
Like echolocation, almost.
By analyzing the deflection pattern of the ping-pong balls, you can mathematically reconstruct the exact shape of the invisible object. In quantum mechanics, we branch into two main computational diversions to handle this math.
What are the two branches?
If we are throwing low-energy particles, we use partial wave analysis, which relies on the accumulation of angular momentum phase. If we are throwing high-energy particles really fast, we use the Born approximation, which treats the scattering as a 3D Fourier transform.
Let's look at the first principle here. Combining an incident plane wave from infinity with an outgoing spherical wave. What does that picture look like?
Imagine a perfectly flat, infinite wall of water, a plane wave rolling across the ocean. That is our beam of incoming particles, mathematically represented as traveling from negative infinity.
Okay, a flat wall of water.
Then, it hits a rock jutting out of the water, the target potential. When the flat wave hits the rock, it creates a new, circular, rippling wave radiating outward in all directions. That is the outgoing spherical wave, modulated by a scattering amplitude.
The total picture is the sum of both.
The complete state of the system is the sum of these two. The flat incoming wave plus the radiating scattered wave.
And the goal is to resolve the target structure from that scattered wave. The materials map scattering cross-sections to phase shifts or 3D Fourier transforms. Break down the low-energy extreme first. It says, as collision energy approaches zero, only the swave can penetrate the centrifugal barrier. What is in swave?
In partial wave analysis, we imagine the incoming flat wave is actually made up of infinite concentric cylinders of angular momentum, which we call partial waves. The swave, P wave, D waves, and so on.
Like layers of an onion.
As the incoming particle approaches the target, it feels the centrifugal barrier pushing it away, which gets stronger the higher the angular momentum. It's like trying to hit the bullseye on a spinning dartboard. The further out you aim, the harder it is to hit the center.
Because it spins you away.
If you turn the collision energy down extremely low, approaching zero, the incoming particles barely have enough energy to overcome even the weakest barrier. The leverage here is immense. The mathematics prove that at ultra-low energies, every single higher-order wave bounces off harmlessly.
So only the center hits.
Only the wave, which has zero angular momentum and hits the target dead center, has any chance of interacting. The infinite complexity of the scattering equation beautifully simplifies down to evaluating a single solitary phase shift parameter.
But there is a falsification filter here, too. The text warns, if a target's potential decays too slowly, like the long reach of the Coulomb force, the standard spherical wave assumption is invalidated. The phase shift diverges. Why does it diverge?
This is a critical boundary condition. The entire premise of standard scattering theory assumes that the target is localized, that once the particle bounces off and travels far enough away, it no longer feels the target's force, and the outgoing wave becomes a perfect free spherical wave.
It has to escape to infinity.
But the Coulomb force, the electrical attraction or repulsion between charges, decays at a rate of 1/r. That is agonizingly slow. In fact, it decays so slowly that an outgoing electron technically never escapes the influence of the target proton.
It's always feeling the pull.
The mathematical integral used to calculate the phase shift diverges to infinity. The standard logic gate is triggered, falsifying the use of basic partial wave analysis.
So the math is filtered out.
The standard theory is filtered out, and physicists must branch into a highly modified, infinitely corrected Coulomb scattering theory to deal with the fact that the scattered wave is eternally distorted by the target.
So if that's the low-energy phase shift method, what happens at high energies? The notes mention the Born approximation and Lippmann-Schwinger equations for weak, fast scattering. How do we decode information from deflection there?
When you fire a particle at extremely high velocity into a relatively weak potential target, the particle is moving so fast that it barely has time to interact. The deflection is minimal.
It just blows right through.
This allows us to trigger a branching decision into the first Born approximation. We assume the incoming plane wave is practically undisturbed, and we only calculate the single first-order bounce.
And what does that math reveal?
The mathematics of the Lippmann-Schwinger equation combined with Green's functions reveal something breathtaking. Under these conditions, the scattering amplitude, the pattern of where the particles bounce, is exactly equal to the three-dimensional Fourier transform of the target's potential energy field.
Wait, hold on. Let me make sure I'm grasping this. The data we get out of a multi-billion-dollar particle collider is literally just a Fourier transform of the inside of an atom.
Yes.
And we just run an ultimate Bayesian update. We collect the scattering data where all the particles landed on the detectors, we apply inverse Fourier transforms, and we instantly update our prior models of the completely unknown internal shape of the target.
Exactly. We mathematically unweave the bounced particles to reconstruct the shape of the invisible rock.
I have to stop the show right here for a second, because this delivers a metacognitive truth that is just staggering. We can never see the microscopic world. Objective knowledge of matter is entirely decoded from how the flow of momentum is deflected by hidden potential fields.
It's a sobering thought for physicists.
Are you telling me that every picture of an atom, every diagram of a nucleus in a high school chemistry textbook is essentially a lie? We've never actually seen any of it.
It is a necessary representation, but yes, it is not a photograph. Everything you know about quarks, gluons, the nucleus of the atom, no human has ever looked through a lens and seen them.
They aren't little colored spheres.
They do not have color or solid surfaces in the way we understand them. They are purely mathematical reconstructions. The objective reality of the subatomic world is not an image. It is a decoded shadow of momentum deflection. We throw math at the dark, and we measure the math that bounces back.
That is incredibly heavy. We are literally blind, just feeling the universe through math. But it perfectly prepares us for the final, most mind-bending concept of this deep dive, the entanglement limit and the system reconstruction of the no-cloning theorem.
This is the big one.
It is time to talk about the total eradication of hidden variables and classical trajectories, the death of local realism.
If the previous concepts stretched your intuition, this final section will shatter it entirely.
The notes start by introducing the density matrix as the new tool to handle incomplete information. Why do we need a new tool? Why isn't the wave function vector enough anymore?
The pure wave function state vector, the kit we discussed earlier, implies that we have maximum perfect knowledge of an isolated quantum system.
But systems aren't perfectly isolated.
In reality, systems interact with their environment, they get messy, they lose information through a process called quantum decoherence. If you only have partial access to a system, or if you are dealing with a statistical ensemble of particles where you only know the probabilities of different states, the pure state vector fails.
So we need a matrix.
We must branch into the computational diversion of the density matrix. It is a probability-weighted operator. The state is no longer a definitively determined vector. It is a matrix that perfectly encapsulates our incomplete classical ignorance layered on top of the intrinsic quantum uncertainty.
It lets us calculate with our own ignorance.
It allows us to calculate expectation values even when we don't know the exact pure state of the system.
And this leads right into the first principle of entanglement. Composite systems separated by space cannot be mathematically factored into independent states. They are a single, non-local entity.
Yes.
We've all heard the pop science version of entanglement, spooky action at a distance, but what does that mathematical inseparable nature actually mean?
If I have two distinct classical objects, like a red book and a blue book, I can describe the state of the red book completely independently of the blue book. But if two quantum particles interact and become entangled, their combined wave function becomes a unified mathematical structure that cannot be factored out. Imagine an algebraic equation like x squared plus 2 pi psi plus y squared.
Okay, basic algebra.
That can be cleanly factored into x plus y times x plus y. But an entangled state is like the equation xi psi plus 1. You cannot mathematically separate the x from the y. They're fundamentally intertwined.
You can't separate the particle.
Even if you separate the physical particles by light years across the galaxy, the Hilbert space vector describing them remains a single, indivisible entity. You cannot specify the state of particle A without referencing particle B.
Which brings us to the ultimate clash of philosophies. Einstein famously hated this. He believed in local realism and hidden variables. The idea that the particles actually possess definitive properties all along, like a pair of gloves separated into boxes, and we were just ignorant of them until we measured them.
Einstein wanted the universe to make local sense.
Our materials detail mapping classical local realism to the statistical limits of Bell's inequality. Walk us through how we break the Bell boundary.
John Bell devised a mathematical theorem that forced reality to answer the question once and for all. Is the universe fundamentally localized and determined, or is it non-local and entangled?
How did he test that?
He calculated a strict statistical upper limit, an inequality, based purely on the assumption of local realism. If Einstein was right, and there were hidden variables predetermining the outcomes of measurements, then the statistical correlations between measurements of two distant particles could never exceed a certain strict boundary limit.
And what was the limit?
The limit is mathematically represented as the number 2.
So the absolute classical boundary of reality is 2.
Let's look at the extreme leverage quantum mechanics applies here. Quantum mechanics predicts that if you take two entangled photons and you carefully choose specific polarization measurement angles that are skewed relative to each other, you can maximize the quantum interference.
And what happens when you run that math?
When you run the quantum mechanical math for those specific angles, the correlation result is 2 times the square root of 2.
Which is about 2.82, which is strictly greater than 2.
By breaking this boundary, quantum mechanics mathematically proves that quantum correlation is undeniably, demonstrably stronger than any possible classical connection.
We actually tested this, right?
When experimentalists like Elaine Aspect actually ran these experiments in the lab, the data consistently violated Bell's inequality, perfectly matching the quantum prediction of 2.82.
And the falsification filter here is absolute and permanent. Experimental data deviating from Bell's inequality permanently falsifies any theory relying on local hidden variables. Einstein's local realism is dead.
It is the most profound falsification filter in human history. The universe strictly rejected local realism. There are no hidden variables. The entanglement is real.
The universe is officially spooky. The notes also mention another boundary here, the no-cloning theorem, the absolute prohibition of copying pure quantum information. If particles are entangled and instantly correlated, why can't we use that for faster-than-light communication? Because if we could, we'd essentially have instant galactic cell phones.
The no-cloning theorem is the universe's ultimate firewall against paradoxes. It's built-in digital rights management for reality.
DRM for reality. I like that.
The mathematics of quantum mechanics is perfectly linear.
Yeah.
If you try to invent a hypothetical quantum copying machine, a mathematical operator that takes an unknown pure state and produces 2 identical copies of it, the linearity of the math creates a devastating contradiction.
It crashes.
The required transformation matrix collapses. It proves that you absolutely cannot perfectly clone an unknown quantum state. Because you cannot clone the entangled states, you cannot force the entangled particles into a specific configuration to send a Morse code signal faster than light.
It prevents us from breaking causality.
The universe allows instantaneous correlation, but strictly prohibits the instantaneous communication of usable information.
So let's talk about the famous Einstein-Podolsky-Rosen paradox, the EPR paradox, and how our materials frame it as a Bayesian update. If there's no physical signal traveling faster than light, how does particle B instantly know what happened to particle A?
This is where framing measurement as a Bayesian update beautifully resolves the conceptual paradox. When you measure particle A on Earth, you do not send a physical collapse signal through space to particle B on Mars.
There is no radio wave.
There is no faster-than-light radio wave. Instead, you possess a prior entanglement model, the single unified wave function of the system. By measuring particle A, you gain local information. This new information instantly updates your conditional prior probability regarding particle B from a spread of possibilities to an absolute certainty.
So the wave function only collapses for me.
The state of particle B collapses instantly from your perspective because your informational model of the universe was instantly updated. The connection isn't a physical wire. It's the shared informational logic of the entangled Hilbert space vector.
This leads to the ultimate metacognitive paradigm shift to wrap up this concept, and really our entire deep dive. The universe is not a bucket filled with isolated objects. Local realism is dead. A physical state is not an absolute property carried around by an object. It is merely a localized expression of a universe-spanning, indivisible field of entangled information.
Everything we consider a separate, physical thing is fundamentally an illusion of perspective. The foundational reality is a single, interconnected web of quantum information. When you interact with an object, you are not touching a localized marble. You are perturbing a node in a universal network.
I am taking a very deep breath right now. Because if you, the listener, have stayed with us through this, you have just completed an immense intellectual journey.
You really have.
We started by stripping away the comforting illusion of solid marbles and baseball trajectories. We mapped the universe as shifting fields of probability density. We watched the universe ruthlessly filter out infinite equations to stabilize reality. We offloaded impossible calculus into elegant algebra and climbed the energy ladder down to the vibrating zero-point energy of the vacuum.
We covered an astonishing amount of ground.
We proved that atoms aren't mini solar systems, but vibrating 3D geometric standing waves. We learned that the universe literally subtracts fermions into absolute zero to prevent matter from collapsing on itself. We bypass complex physics entirely by relying on the sheer perfection of group symmetry to dictate conservation laws.
It's all just geometry.
We learned how to approximate reality by adding tiny tuning factors to idealized models, and how to guess the ground state by squeezing calculus derivatives. We saw how all objective knowledge of the microscopic world is just decoded shadows of scattered momentum. And finally, we just proved that local realism is a lie, and the universe is an indivisible, entangled web of mathematical information.
It is a profound realization of what it actually means to exist. And to conclude our analysis today,
Yeah.
I want to offer one final provocative thought specifically designed to linger with you.
Okay, well, yes.
We have spent this entire session establishing that objective reality is fundamentally just mathematical information deflecting off potential fields, and that local, independent objects don't truly exist independent of the whole.
Right.
If that is true, if the universe is just a unified, non-local quantum information processing structure, what does that mean for the biological neural networks in our own brains currently trying to understand this information?
Oh, man.
Our brains are made of these exact same entangled fields, governed by these exact same Schrödinger equations. Are we, as conscious observers, truly separate entities studying the universe from the outside? Or are we simply the universe's mathematical source code organizing itself into a localized structure for the sole purpose of trying to read and comprehend itself?
Are we the universe's source code trying to read itself? That is going to keep me awake tonight, and honestly, it should keep you awake too. Thank you so much for sticking with us through this intense, reality-breaking deep dive. We asked you to abandon your intuition, and you did. Take these concepts, look at the world around you, the chair you're sitting on, the light hitting your eyes, and remember the hidden, entangled mathematical architecture pulsing just beneath the surface. Keep questioning the nature of the reality around you. We'll see you next time.